Hi, welcome back to Moose and Chemistry. Okay, today's lesson is on the quantumization of energy. In other words, how to calculate a photon's amount of energy according to color and like it. Well, you know what? We've been talking a lot about electromagnetic radiation in the spectrum. Well, here's another really cool thing for you. E equals HV. All right, that's a new equation for us, and let's define it first. E is energy in joules. All right, so we got that. H, that's Planck's constant. Now you think about it for a second. Planck's constant, is that something from Ed, and Eddie? You know, Planck, that ridiculous mascot thing that kid drove around as his imaginary friend? No, that's not the kind of Planck we're talking about. Actually, what Planck's constant is, it relates the energy in one quantum, a photon of electromagnetic radiation, to the frequency of that radiation. What? All right. Simply put, it's got a number to it. It's 6.626 times 10 to the negative 34 joules per second. Oh, wow. Okay, now I understand it. Yeah, right. And then, of course, there's V. Let's not forget V. V equals frequency. All right. Okay, so we're going to make up a problem, and maybe by doing this problem, we can understand this a whole lot better. So in essence, what we're trying to do is we're trying to see how much energy is in a photon, because different colors have different wavelengths, which means they have different amounts of energy. And so we're going to use Planck's constant, remember, relates the energy in one quantum of a photon of electromagnetic radiation to the frequency of that radiation. Okay, maybe we're getting a little bit better with that. All right, so let's go ahead and figure out this problem here. What is the energy, okay, of a photon, okay, sounds good to me so far, of green light? Well, this is a really great thing you could do on the weekend with your friends, I bet, right? You make a lot of good friends that way. Ah, come on, you know you would. Frequency, frequency of 5.75 times 10 to the 14th hertz. You know what? That 10 to the 14 hertz tells me that's in the visible light section, because 10 to the 14 hertz is in the visible light section. All right, so what do we know? Okay, we know H, which is Planck's constant, not the board that kid carries around, Ed, and Eddie. All right, so it's 6.26 times 10 to the 34 joules per second. Our frequency, wow, we got that right up here. Yes, it's 5.75 times 10 to the 14th hertz. Okay, so we got our frequency, and now we're just looking for the energy. Oh, wow. You know, this doesn't really seem really hard. Oh, well, we're not going to use a 3 there. I don't know why I drew that 3 there. I was trying to do a question mark. All right, riddle me that, huh? So anyway, so we're going to go E equals HV. So energy equals 6.626 times 10 to the negative 34 joules per second. All right, so far, so good. And we're going to multiply that by our frequency, which is 5.75. Okay, make that a little bit better so you can see it there. It's not really helping a whole lot. Let's see. Let me get that. Okay. All right, and then we'll make that a 5 a little bit better, times 10 to the 14 hertz. Okay. Now remember that hertz is the same thing as 1 over negative s. So I'm going to go ahead and change that hertz thing, because I want to make this a lot easier to see it. So we're going to go 1 over s minus 1. That's right, hertz equals 1 over S minus 1. Go figure, right? Okay, so now we got this. Boom, boom, there go our S's. Gone. So we just do our calculations. So let's take our calculator here, and let's put this in 6.626. That's Planck's constant minus 10 to the negative 34 times 5.75 exponential 14. And lo and behold, we get 3.81 times 10 to the negative 14. So the energy in one photon of green light has this much energy. 3.81 times 10 to the negative 19 joules per photon. Now, you know what? I bet if we did this problem in different wavelengths of light, we would find out that the energy was different. So the color of light is related to the energy that's produced by the photon. Okay, one other thing. Notice that we have E equals HV. Well, what if your problem had the speed of light, for example? What if your problem had the wavelength, but the frequency? So sometimes before we use E equals HV, we may have to use C equals lambda V before we can put that V into that equation there. Well, listen, guys, you be snarly, and we'll see you back here at Moosing Chemistry.